Hey gang, and welcome to another worksheet solutions walkthrough for the worksheet Carbocation Rearrangements. So at this point in time, we've seen SN2, E2, and SN1 and E1. And we know that while SN2 and E2 were concerted one-step mechanisms, not so much with SN1 and E1, right? That was our first kind of, welcome party for carbocations. And we can see that, they're unstable. And I'm sure you've watched this instructional video, we've seen that they can improve themselves because nature loves stability. So this is all about carbocations, how they can rearrange themselves to make themselves more stable. So let's look at the worksheet and get some explanations for the answers for the worksheet. Okay gang, so in problem 1, all we are tasked with doing is drawing the final carbocation, if you will, in each different scenario we're given. So if we look here, we have one of two situations. We either just have a polar product solvent that's going to have, cause conditions for solvolysis to occur, and we'll have a carbocation, or we have an alcohol that is in the presence of a strong acid, and it will get protonated to OH2+, and then it will leave through solvolysis. So one of the two. But it's all about drawing the final carbocation, checking if there's a shift. So what I want to do first is, what I'll show you is how this this will pick up H+, it will turn into OH2+, basically water, and we will have it leave. So my approach here is I'm going to draw the initial carbocation over here, and then we'll draw the final one right there. So initially, the carbocation I am going to form is this, the secondary one. Now, pause. Can we improve this either through a hydride shift or a methyl shift? I hope you're thinking there's no benefit to hydride shift from here, move the carbocation secondary to secondary, but up here at tertiary, we do have a situation. So if I draw this hydrogen right there, remember it's a hydride shift. So you're moving, I'm gonna move the plus over here. You are moving hydrogen with two electrons in this bond to bond to that carbon right there. So you're literally moving H with 2 electrons. So the result is the final carbocation we will produce is this tertiary one after the secondary one rearranges itself. Okay? Now, over here. This is just straight up solvolysis with bromide leaving. So the first carbocation we create is this secondary one right here. And I think you're seeing there's no benefit to go secondary to primary, but there is a benefit secondary to tertiary. And we will do that through yet again another hydride shift. Remember, draw that arrow from the bond to the carbon because you're physically moving the bond along with the hydrogen. So this is our carbocation. Now to here. Remember, this is a situation where this will get protonated by HCl. So we end up with OH2+. I'm going to draw, erase those arrows. This will leave through solvolysis. The initial carbocation we make is this right here. Now remember, secondary to primary does us no good, and we don't even have any hydrogens to the left of us to do a hydride shift. However, this is a quaternary carbon. Let's do a methyl shift. Instead of moving H-, let's move a whole dang CH3. So our final carbocation will look like this. And the benefit there is we went from secondary to a tertiary carbocation. So net, there is a benefit. Moving on, initial carbocation over here with this chloride leaving is, I realized I kind of drew that obnoxiously large. And I think you can see we will have a benefit of going from secondary to tertiary via a hydride shift. So we have this going on. Oh, I'm all screwed up. Okay, so these two are connected. And I'll show you the shift real quick. The reason I chose this problem to draw it this way is that, you might say, oh, but then you can do a methyl shift, but it won't matter. There's no benefit from going tertiary to what will then become tertiary. Just do the one hydride shift. And last but not least, another situation where we will protonate the alcohol to a good leaving group, which is water. It will leave. The initial carbocation looks like this. And I think you can see No benefit from going from secondary to secondary here. However, we can get a tertiary carbocation by doing a methyl shift. Final carbocation looks like this. Positive charge is here because that is the carbon that lost the bond through the rearrangement. Okay, that is the first of 3 problems. So let's go to problem 2. Okay, gang, so in problem 2, we're actually tackling a mechanism that, from my experience, the textbook I used in jOeCHEM is in the alcohols and, alcohol derivative section of the book, not so much with SN2, E1, E2, SN1. However, it's an E1 mechanism, and you're all smart. I know you can handle getting a glimpse of the future right now. So, in this problem, we need to draw the mechanism and then explain why the shift occurred the way it did. And you'll see why it might be a little bit of, why it might warrant an explanation when we draw the mechanism. So, nothing new here. I hope you can see right off the bat a couple of things. Not a good leaving group to start. However, this OH, this alcohol, is in the presence of strong acid. So we'll get protonated up to OH2 plus water. So this bad leaving group will get turned into a good leaving group. Then I hope you're kind of seeing there's an alkene in the product. Okay? So I'm in a polar protic environment. I will have a good leaving group. Solvolysis will happen. I produced an alkene. And we have heat. This has E1 written all over it, right? Because high temperature favors elimination. And in this circumstance, right, not only are we favoring elimination, but we are in a polar protic environment, right? So we're forming carbocations. So this is E1, not E2, and we have everything we need, right? We can protonate this up to a good leaving group. We have the heat. We're forming an alkene. It's an E1 mechanism. This is, if you want to give it a formal name, dehydration with sulfuric acid. So yeah, there's actually a video in the alcohol derivative section of jOeCHEM. So really quickly, we're going to draw the mechanism. So first and foremost, we can't do solvolysis until we have a good leaving group. So the first thing we're going to do, and I like to draw sulfuric acid like this whenever I use it, so it's not super large to draw, but it's H2SO4. Okay. So we're really just doing an acid-base reaction. The alcohol is grabbing H+. So in this step, we now have OH2. Formal charge in the oxygen is a plus. If you want to draw it, you can have the you can include the conjugate base, the bisulfate. Not necessary really, but you can if you want to. And the reason you might is because you can then reuse this as your base. Let me separate this a little bit to do elimination. So before we get there, this has to leave. So this is your solvolysis step. Now we have a carbocation down here on a secondary carbon. Now we have to pause and think to ourselves. So clearly a rearrangement happened. We need to figure out what exactly happened. It makes no sense to rearrange over here because that's secondary to secondary. And while it looks like it won't make sense to rearrange secondary to secondary, that's what we need to do. So we need to expose a hydrogen. We need to do a hydride shift. And while this never really makes sense to go from the same situation, carbon substitution wise, to the same situation, I mean secondary to secondary, the reason it makes sense is because when we do that, we now have the ability to eliminate and form a better, more stable double bond. Instead of either having the option of secondary for a double bond or secondary, right? A di-substituted double bond. Now we'll be able to form a tri-substituted double bond. So when we bring back our bisulfate base, we can take the hydrogen up here, eliminate, form the double bond here, and I am kind of getting a little ahead of myself in terms of the explanation. So here's the mechanism, right? Protonate the alcohol to a good leaving group. Solvolysis occurs because we're in a polar protic environment. Your carbocation is formed. We can shift, right, because we see up here that we have to pretty much involve these carbons, and our carbocation's here, so it makes sense we have to shift up, right, to form the double bond. But the reason being I would say like shift from, I would say secondary carbon to secondary carbon, spelling, occurs to form more stable double bond. So that would be nature's driving force, right? A seemingly equal shift happens so that you can form a better double bond in your product. Okay, problem 3. Okay, gang, so if you seemed a little scared when you looked at problem 3, don't worry about it. It's one of those problems where it looks crazy. You're like, how did we go from 5 to 6 in the ring? But don't worry, I promise you know everything you need to actually solve this problem. So, when you see something like this that kind of spooks you, just stay calm and pick out the things you recognize. So, we have an alcohol, and we are in a polar protic environment with a very strong acid, so this can make this into a good leaving group. We have heat, and we see evidence of an elimination reaction occurring. So this is just another E1 reaction. It's a dehydration reaction with sulfuric acid. Dehydration because we drive water off, H2O, forgot to mention that. And if you're also wondering what reflux is, don't worry, that's just a lab technique. It's what's commonly written over the arrow for a dehydration with sulfuric acid reaction. So it's nothing you need to worry about. It's just like a real life thing. So with these problems, just start and slowly make your way through it, and then eventually you will find what I would call the light bulb moment. Okay? So first and foremost, let's protonate this alcohol to water and make it a good leaving group. So again, I'm going to draw sulfuric acid like this just so I can go ahead and interact and grab H+ with the oxygen and the alcohol. So I'm going to draw this over here. We produce bisulfate, which we will need as a weak base later. And we now have, actually that was fine. We have our substrate, which now has a good leaving group. We have water, we have a plus charge on the oxygen. We went from hydroxide being our leaving group to water being our leaving group. So at this point, we can actually have solvolysis occur. This will go ahead and leave. I'll abbreviate that, solvolysis. So let's take a look. We formed our a carbocation, so let's pause. This might be a situation for us to actually make something happen, right? We have a secondary carbocation, and one thing we could do is, through a rearrangement, maybe we can go from a better cyclic situation, right? 5 carbons to 6, right? And have 0 ring strain, because 5 has a little bit of ring strain. So what we can do is actually take either of these bonds and rearrange it. It's like a methyl shift, if you can think of it that way, but the driving force is that we're expanding our ring to a better conformation. So since we're going to expand from a 5 to a 6-membered ring, what is going to be helpful is if we can do 1, 2, 3, 4, 5, and 6, okay? So let's go ahead and draw the skeleton of our ring. So 1 and 2 will be connected. Actually, sorry gang, I always do this. Let's do the running connection. So 1, then 2, 3, 4, 1, 2, 3, 4, counting is hard, to 6, okay? So 6 was commonly attached to 2, but now it's going to go to 1. So if I go 1, 2, 3, 4, 5, and 6, this is going to help us kind of figure out, make sure we get that methyl group attached in the right place. So if I just go like this, I probably made this more complicated than it needed to be. Sometimes it helps in more complicated situations, but we've essentially, if we just had this 2, 3, 4, 5, 6 ring right here, they would all be connected, but now 6 is no longer attached to 2, 6 is attached to 1, and I hope you can see that through all of this, this dotted carbon right here, 2 is no longer attached to 6. 2 lost a bond, okay? So we actually have a carbocation right here because 2 only has 1 hydrogen. 2 still only has 1 hydrogen. So 2 is now the carbocation. So even though we went from secondary to secondary, we improved our ring situation. However, now look at this. Can we still make this better? And the answer is yes. We can do a hydride shift. So I like this problem because it shifts to improve the ring conformation. It also shifts afterwards to do, so I'll do methyl shift, methyl. And this is hydride. So we have two shifts here to then get a tertiary carbocation. So now we can then proceed with this mechanism, which is going to be, dehydration with sulfuric acid. So we can bring our bisulfate back. I can expose a hydrogen, doesn't matter which one, right? Because on either side of our tertiary carbocation, they are equivalent. I can abstract the proton, electrons swing down. So I finally produce the product. So let me go over that one more time. So we have two shifts in this problem. But again, you didn't need to see it right off the bat, nor should you have been able to see it right off the bat. We have, if we assess our situation, we have something that can be made into a good leaving group, and luckily we're in a polar protic strong acid situation so that we can improve it. We have heat, and we see we have evidence of elimination product, so this is an E1 reaction. First step is we protonate our alcohol up to being a good leaving group, water. Then through solvolysis, water leaves. We have a carbocation. One thing we can do, and we see the evidence of it, is that we have a 6-membered ring. So we can do a methyl shift type deal to include this carbon into our ring, going from 5 to 6, improving our overall ring stability. Then we have a secondary carbocation. Nature will quickly switch that over to being a tertiary carbocation through a hydride shift. Then we actually do the elimination to get our final product. Okay? One more problem, gang. Let's finish the worksheet strong. Okay, gang, to finish this worksheet, we're going to actually complete the reactions for these right here. And, now that we have our shifts down, we obviously have to bring stereochemical considerations back into the mix. So, if we take a look here, we obviously see, this is a dehydration with sulfuric acid reaction. It's E1. So, first and foremost, let's figure out what carbocation we are working with is. So the initial carbocation, right, we know we're going to protonate this up to water. Then this will leave through solvolysis. So far over here, just like we did in problem 1, my initial carbocation is this secondary carbocation. I hope you can see that we will methyl shift over. So the carbocation we are working with is this carbocation right here. Okay? So the double bond will go between these two because that is the most substituted double bond. Our product is this alkene right here. Okay? Problem 2. So right off the bat, we can see that we will have, so this will get protonated up to water by HBr. This will leave. So our initial carbocation is this right here. Now, this is an E1. This is SN1. We will be attacking with Br minus. The question is, can we improve this carbocation before we do that? The answer is no, right? It's maybe one carbon away. You won't do a secondary to tertiary shift, right? We only did that in the E1 problem because we could make the better double bond. We didn't double shift, right? So that secondary carbocation is going to stay put. However, don't forget, when we attack with Br minus, we can attack here, or we can attack there, right above and below. So we will have a racemic mixture because you'll see that when we attach this bromine like this, stereochemistry matters, right? Because we are attached to 4 different things. So you could either wedge this and then draw the other enantiomer with a dash, or if you remember, if you want to be Joe Cool, you can use that squiggly line to say 50% this will be a dash, 50% this will be a wedge. Just for complete clarity, I'll go ahead and do this for now. You can write plus enantiomer. And if you want to be extra careful, you can do 50%, 50%. Okay? No shift there, just remember to reflect stereochemistry, right? The stereochemical ramifications of doing SN1. All right, so over here, this is just a classic good leaving group, bromine in a polar protic solution of water. It will leave through solvolysis. Our carbocation will look like this. I hope you will see we have a tertiary carbon next door with a hydrogen that is ready to be shifted over. And absolutely it will. Oh, whoops, so this will shift. Let me redraw this just because I'm working with limited real estate in the board department. It is there that water will attack. Now remember, we don't really have to worry about stereochem because I will have my water attached here as an OH, an alcohol, right? And this isn't a stereo center, right? Because we have a methyl group and a methyl group, so we're not attached to 4 different things. That's not a chiral center. So no reason to, have a wedge or a dash, show a racemic mixture. It's an achiral solution, right? So that is your product, okay? Down here, right off the bat, we know this will get protonated to water, and it will leave through solvolysis. So our initial carbocation is going to look like this. Now, I hope you're going to notice, I'm going to leave this wedged. But remember, when we form carbocations, they are sp2, they are planar. So this dashed ethyl group, I'm going to make it planar. Okay? So, it's a tertiary carbocation. Oh, whoops. I skipped a step. This is so I'm going to leave this dashed, oh man, yikes. So, secondary carbocation. We can absolutely hydride this shift over with this wedged hydrogen right there. We will shift it up. Now I can actually say what I wanted to say. We will actually then have a straight line ethyl group because our carbocation is here now on this tertiary carbon. Remember, carbocations are sp2, they are planar. We still have the wedged methyl group, but I hope you'll see the best carbocation we can make is this right here. It's going to be a tetra-substituted double bond. So, when we form this double bond right here, make that a little bit better. This methyl group needs to be straight line. This ethyl group needs to be straight line. So that is your product right there. Last but not least, the initial carbocation is going to look like this because chlorine is going to leave in the polar protic solution of water. We will have a secondary carbocation, and I haven't drawn the full structure. Okay, there we go. This will obviously hydride shift to be tertiary. So the carbocation we are working with looks like this. Let me circle that just because I got a lot of structures floating on the board now. So when water attacked that position, we will stick it right here as an OH. And again, I hope you're seeing we are not showing stereochemistry because this is an achiral center. We have 2 ethyl groups. We are not attached to 4 unique things. Whew, gang, this worksheet, I debated where I wanted to place it on jOeCHEM, but I put it with the SN2, SN1, E1, E2. Because we're already doing carbocation shifts, I don't see any problem giving you this dehydration reaction a little bit early with the ring, the ring shift opening reaction and whatnot. I know you're smart enough to handle it in this way. If you come across it, if you're watching this video and you haven't done it in your class and you come across it later, you already know it. If you're watching this video, that means you've supported jOeCHEM and donated some money, and I'm so thankful for that. I hope this resource is helping you crush organic chemistry up until now and to the very end of your organic career, and I hope to see you all in the next video.